So let's frame this service networking challenge. Is there a problem that needs to be solved here? So I said yesterday, hopefully this doesn't offend anyone in this room, but I don't think so. I said yesterday that you have to have a problem to solve if you're going to build a solution, unless you're a blockchain. And this is not a blockchain. And this is not a blockchain. This is not a blockchain solution. So, and HashiCorp, one of our guiding principles is pragmatism. So what is the real problem that we are trying to solve here? So the reality that we look at and the core philosophy of our business is that mixed technologies, heterogeneous environments are the norm. I said yesterday too, this was very much controversial when we started the company. Within the first couple of years of starting the company, I had a call with an analyst who hung up on me when I said the word multi-cloud because actually, she said, call me when you have a good idea, and then hung up on me, which made it extra painful. But this was the conviction that we had, was that multi-cloud and heterogeneous environments were going to be the norm because change isn't atomic. I mean, at the very least, even if you believe that you could go full cloud, for a real large company, that's going to be a multi-year process. And how do you balance that? And that was our idea, our thought. And so we see these mixed technologies, and I think in the largest companies that you're all sort of a part of or talk to, you see this full spectrum, right? You see companies that have mainframes still, that have cutting edge teams that are using serverless in various places. The full spectrum is available, but the middle tiers are highly contended, right? But the thing that has always connected this and made this heterogeneity work is the network. I think you could be a little more specific and claim that the thing that's made this work is generally TCP. As long as everything speaks TCP, you could work across these boundaries and pretend that the technologies aren't dramatically different. And so the network is critically important to enabling the transition of platforms, the transition of paradigms, and reasoning about these things. And so if we look at a traditional data center, it has this really nice look. It's very clean. It has 4 walls, and you could kind of go north to south and follow the path very cleanly. You go from outside global internet traffic to a external firewall, sort of to an internal load balancer that goes to some front-end web tier, usually back through an internal firewall back to a data tier. There's this very clear north-south thing you can model, and you could reason about networking in this environment. In a more modern sort of deployment scenario, what we're seeing is this. And this is complicated. It's hard to model this without appearing hyperbolic, but this is reasonable for a company, even a company that was cloud first that just adopted Kubernetes, right? Like this on the left might just be EC2 and on the right might be their new Kubernetes. More realistically, for a company that's been around 10 years or longer, this on the left is some hardware they have, and on the right is EC2 or Azure or something, and then now they're adopting Kubernetes. It's getting more and more, but you have your old stuff, you have your new stuff, and it still has to communicate, because the way we describe it is the systems of engagement are moving to the cloud. The applications that need to be deployed faster, the net new workloads, the things that are reaching the user, right? The mobile app APIs, those are all moving to the cloud. But a lot of the core processing systems are not quite there. They're staying where they were. They might still be mainframes. They work. And so you have this communication that has to go back. So you have a networking challenge there. And it sort of goes both ways, right? And this is a reasonably basic thing. Now this slide definitely seems hyperbolic. It seems crazy, where there's this reality. But we talk to, not me personally, but as a company, even at our relatively small size, we get to talk to around 100 to 200 of the Global 2000 on a weekly or bi-weekly basis. We get to do that. And this has surprised me to be more of the norm than the exception. And the way it happens is pretty organic. Is you start with something really clean. You have a new business unit, a new product that decides they want to be more cutting edge. They use Kubernetes. You have that. You have another product or business unit that's decided to contract with Pivotal. So Pivotal comes into the play. You have some customers you want to reach in a different region, say Europe or China, and you deploy a data center there. And you have sort of this complexity that naturally, organically arises. Not to mention mergers and acquisitions, as soon as you bring in another company and try to put that under your corporate umbrella. So more and more, we're seeing a complexity where you have multiple platforms and multiple data centers around the world, and how do you reason about this? And so this is where Consul steps in. And we thought about what can we do to make this simpler? How can we solve this challenge? So Consul is really three features. One, again, pragmatism is a core part of our principles. I think one thing I view service mesh and modern cloud-first networking tools today is they feel like a big bang solution. It's really hard to justify adopting them because it's a lot of work, and until everything is connected to it, you don't extract value. And until you extract value, it's all just cost. And so we like to break things into how do we have a crawl, walk, run adoption strategy. So you could adopt early, crawl, get value out of it, but you're on the path towards this end goal. And I'm sorry.
Oh, you're fine.
So Consul, this broadly is the crawl, walk, run steps of Consul. And the top two bullet points have been features of Consul for almost 4 or 5 years since its release. And the service mesh part at the bottom is newer, and it was released last year, and more where we're heading. But I think that aligns well with what companies are ready for currently. So the first one is being a service registry and bringing in health monitoring as a part of service discovery. And so I think the crawl step is really, can you point out what are all the things deployed in every single platform and where are they right now? And how accurate is that data? Is that IP address correct, knowing that it's scheduled? Do you actually know that's even up and running still? Is it healthy? And so step one is bringing that in. And so Consul does that. It doesn't matter if your services are in PCF or Kube or VMs or in different data centers. We give you a unified view as well as unified DNS and API in terms of discovering these services. And we do active health monitoring of all these things to ensure that when you ask where is the database, we are usually returning where is the healthy database. So step one is getting that catalog. The walk step is more, now that you have this global registry of services that is updated at a millisecond, microsecond scale, and we'll get into how that's possible. When you have this super up-to-date catalog of all your services, you could do some really interesting networking middleware automation. Let's not burn the whole thing down. Let's not say get rid of all your switches and load balancers and everything right now. You already have those. You're extracting value out of them. How do you just make them better? And so the next step we usually see with Consul is let's make the F5 load balancer configuration dynamic. Let's no longer manually update what that thing is pointing to. Let's hook it in with Consul. And we have integrations with Consul and F5 to do just that. And so you have this walk step. You're getting more and more dynamicism and value out of these things. And then finally, at the bottom, it's, you have your service catalog, your network middleware automation is giving you value. Now let's maybe the new workloads, maybe just the Kube workloads, just let's pick some services that are already connected into Consul, and let's start doing zero trust networking between them. Let's do mutual TLS. Let's do intention-based routing rather than IP-based routing. Let's start bringing in layer 7 traffic shaping. But we could do it at an incremental service-by-service basis that doesn't impact the entire data center.
How's this doing the discovery of services? Is it requiring an agent?
Yes. Yeah. And I think in 3 slides I get to the architecture. Do you want me to just jump to it now?
Go ahead and keep going.
Okay. That's a good question then. Yeah. I realize this slide is the hand waving, like, believe me. And we're going to get into the
like, wait a minute. Zero trust? Let's talk more about
You're the
that.
man behind the curtain.
Yeah. I don't want to trick you. So we're going to get into exactly how all this stuff works. So let me just, 2 slides. So
okay.
This slide and the next slide. Quickly on Consul, the service mesh stuff is new. A lot of people, Consul has sort of experienced a lot of growth in the past year, so a lot of people think Consul's new. Consul's actually was initially released in 2014, so it's about 5 years old. You can see some vanity stuff, but roughly tracks how popular it is for some vague definition with GitHub stars and downloads. I think what's interesting is we have paying customers and a large set of users, but we have customers running as many as 50,000 agents in a single data center. So this is proven at a very large scale. And we've shown that both a large number of agents in a single data center as well as low number of agents in a large amount of data centers. We've done both axes. And last year at reInvent, AWS said that 2018 reInvent, they announced Cloud Map for AWS. And as part of that announcement, they actually said that Consul is the most widely deployed service discovery tool on AWS today, which was surprising to us that they would say that, but it's there. So I could say that now. So let's get into the architecture and how this stuff works. And I'll try to make it as simple as possible. Because it is relatively simple. We just put a lot of boxes on this slide. So Consul requires an agent. It has a set of servers, and then it has a set of clients. The clients are the agents that run alongside, generally on the machine, not alongside the workload. So if you're in a Kubernetes environment, you have one per machine, not one per pod. But you have a number of clients, and then you have the servers. The servers form a Raft cluster, and so they perform leader election and log replication, and they do that among themselves. And the clients everything is loosely connected with a gossip system underneath. And the gossip system is only used for membership. So all data is sent over TCP through the servers, then replicated via the servers. But the clients, all the membership is via gossip, and all the health data is via gossip. And that's how we're able to get that health data so quickly. When you bring in multiple data centers, which we've had since version 0.1 and continue to push, you run a server cluster per data center. So you have separate RAF quorums per data center, and we do a separate gossip pool across all the data centers in the world. And the open source version is it requires a fully connected network, and in our enterprise version, we actually support hub and spoke and other models for this. But it's effectively a WAN gossip. And so what this does is eventual sort of consistency between the two things. The things that need strong consistency, like ACLs and so on, will do a direct TCP connection from one data center to the other to pull that data in, cache it in your data center. But this is the high-level architecture of how things work. And I'm going to dive into lower level to how the performance and...
Are there any options besides clients, like SFlow or anything else? Because some customers don't want clients.
Yeah, so we actually have a couple different. All the clients are doing, and the clients are doing a lot, but the clients are just hitting a publicly exposed API and providing some machine health checking, which is beneficial. If the machine is down, we consider the unhealthy. We consider the services also unhealthy. If you don't need that, you could actually just hit the API directly, register it externally. So we actually have, for devices like F5, we're not going to run an agent on the hardware device. So we have something called the external service monitor, and that can run anywhere, and it sort of watches it externally and registers it externally. So that could represent a number of services, and you don't need the agent. But as you'll see, there's a lot of benefits to the agent, so we highly recommend having that there, and it's very lightweight. Yeah.
And to piggyback on that, I think where you were going with this is the being able to tap into that API and say, these servers are running these basically ports, and it monitors them.
Yeah, exactly.
That's exactly what it does. So you can automate that, things like that.
Well, I'm thinking the same type of approach is, you use the F5 as an example, but I think of healthcare or some other organizations. I've got MRI machines or plasma pumps or various hardware devices that are ancient in some cases, and I have to keep running them. I can't do anything about that, but I can't load anything on them because either they're too ancient or there's just not a mechanism or ability to do something like that.
Yeah.
Do you get a granular level of visibility inside of that agent, interrogator, or are there other ways of trying to handle that type of approach for just devices that will never be able to load an agent into?
Yeah, for these, the ESM external service monitor is the right approach. It's just a lot more explicit. You have to tell the ESM what's the node name that it's on, and what's the service, and what's its address. And you have to tell all those things, whereas with the agent, we can implicitly figure all that out for you. There's some performance trade-offs too, but that's the idea.
Not as dynamic.
Not as dynamic, yeah, it's a good way to put it.
But at least it's a solution for those devices.
Totally.
Otherwise, wouldn't have an option for that, which is nice.
Absolutely, yep.
In a lot of regards, this just seems like DNS. So what is it basically DNS under the covers, or is there something more sophisticated going on over what you could do with DNS and SRV records?
There's a lot more sophistication of what is possible, but I think in terms of, we expose service discovery both as an HTTP API and gRPC now, but as well as DNS. And the reason we do DNS and Consul ships the DNS server into it is that it's the lowest common denominator to make this work with everything. And so it's the crawl step of you don't need to rewrite any applications, almost all applications except DNS. So you don't really need to rewrite almost any applications, and you could get this dynamic service discovery immediately. But as you adopt more complex features, you may need to move away from that. But we support, let me just move back here, because we support stuff like, we have this feature called prepared queries, where you're able to, does what you'd expect, I guess, but you're able to augment the DNS rule or custom resolution, where you're able to change the way DNS works. The default way DNS works is you say, where's the database? Just looks up the databases and return them to you. You could introduce custom logic there, where if you say, where's the database, you could actually do, where is the database with the lowest latency from me? Or where, if that's not available, fail over to this data center first, then this data center. You could introduce custom logic, and we resolve that and return it through DNS. So it's not a straight host lookup.
And in that custom logic, can you make it to where it actually sees that it's resolving and working, as opposed to, here's my DNS server, it pings, DNS is down, but it pings, therefore I'm never going to go to secondary because it pinged.
Exactly. So as part of the agent, as part of a service registration process, you attach health checks to it, which could be as dumb or as rich as you want. And the default behavior for DNS is to only return the things that are healthy. The challenge there, which especially in 2014 was a key innovation for Consul, was at a scale of 50,000 agents in a data center, how do you avoid sort of an n squared or star topology health check issue? And how do you make that scale? And I'll get to that. So the gossip is key to that.
Now, quick question. Network monitoring and network services monitoring, that is a really crowded space. What is your number one key differentiator?
We're just holding the data and propagating the data. You could use whatever tool you want to actually do the monitoring yourself. So when you register those health checks, we support executing a binary, reading from a file, an actual something else will tell us. We support a number of things, and so we're not trying to be a full-fledged monitoring solution. We're just trying to make sure that our catalog has that data in it to make these informed decisions. So I'd say we're symbiotic with them for the most part. Cool. Couple more on the architecture here. So the deployment of Consul is that it's written in Go, and so this gives us the benefit of being a single binary solution. And in general, for HashiCorp solutions, this has been a big selling point for us, is that to run Consul, you don't need to run a separate database. You don't need to have all these config files. It's really just one binary, one file, sort of get going. The single binary has, just depending on the flag, either puts it in server mode or client mode. So again, it's the same binary wherever you are. You run 3 to 5 servers per data center, and we have built-in multi-data center support. Okay, so yeah, to go over how the servers work, and then we'll get into the LAN gossip, just diving in. I think I mentioned this already. They form a raft cluster, so they replicate state, they perform leader election, but this is also where all the data is stored, right, in the raft logs. And so the agents cache data, as we'll see, but the source of truth is the servers, and you're able to say I need strict consistency, or I could be relaxed and have stale consistency. You're able to do that on a per query basis, but that's what's really happening. We store all the service catalogs, key value, all sorts of stuff right here in the server clusters that's local to each data center. Okay, so here's where the clients come in. So we have these servers, and we ask you to run these agents on the machine. What the clients actually do is expose the full API of the servers locally. This solves the service discovery 0 problem. How do you discover the service discoverer? The answer to that is it's expected to always be on loopback on a certain port. So 127 port, whatever, that the agent's always there. So everything that integrates with Consul tries that first unless you configure it otherwise. So that solves that initial problem. So the app will do the DNS, and the DNS resolver is local. So if you configure your DNS resolver to resolve Consul top level domains to that, it's a local DNS server. It's not reaching over to the server. This is important for the resiliency of the cluster. So we expose the stuff. I think we show, yeah, and then that sort of forwards it to the right server, so that the client handles who's the leader currently, who should I talk to. For you, the app only has to talk to loopback. We support this thing called blocking queries. So the app can perform a number of blocking queries to say, tell me when the healthy instances change. And they open a long connection to the local client. And all these long connections, you could open a lot of them, because what they do is there's thousands of connections to the local agent, but we multiplex that onto a single blocking query back to the server. And so you have all these complex sort of waiters, more or less, at the local level. But if you have 50,000 servers, to the servers, 50,000 VMs, let's say, to the Consul servers, that's just 50,000 connections, which is super manageable. Yeah, I think one thing that isn't mentioned here, which is more important for the service mesh stuff, but there's also a mechanism by which the servers can push data out to the agents. And so when you do a DNS lookup with custom resolution with these rules that are like, give me the lowest latency database and failover and things, you're not paying that resolution cost on every single discovery, because that would introduce probably hundreds of milliseconds or at least 100 milliseconds on every single DNS. Instead, the client is able to say, you're asking for this a lot. I'm just going to ask the server to tell me when that changes. And when you ask for this, it's just a static. It's in memory. It's like here. So it's microseconds on the resolution. It's instant. So that's the benefit of the agents and why you would want to run them. They do all these performance caching and multiplexing of connections and things to lower load on the servers. So the other problem is sort of just knowing who's in the cluster. So we're forming this huge cluster. And how do you keep that stable? How do you join it? What's that like? To handle membership and health checking, will come into it, we use a gossip layer underneath. And so this is based on UDP. It's super lightweight. Sort of the papers and the deeper architecture, what we did is online. But the reason we chose this is that it doesn't have an n-squared growth problem as you add servers. It's a constant add as you add more servers. So this handles cluster membership failure detection. I think there's slides that go into this. There isn't. So let me just explain this real quick. No. Okay. So the way this generally works is that the agents at the edge are doing all the health checking. So when you say, look at this service, or read this file, or run this shell script, the agents are doing it. We only send data back to the servers on a edge change, right? So if it goes healthy to unhealthy, unhealthy to healthy, then we update the global catalog. So this keeps that sort of constant split of load across your entire cluster. When servers, the other problem is sort of as servers come and go, how do you know if the server's not saying anything? How do you know is the lack of data mean everything's good, or is the lack of data mean the server itself is actually down? And this is where the gossip protocol health checking comes in. The protocol we built on top of is called SWIM, and it's an infectious sort of epidemic style membership system. So what we do is every second, or it's tunable, but roughly every second, one server picks 3 other servers to just send a quick UDP packet and say, you good? And 3 servers respond back to it. If the UDP packet fails, we fall back to TCP just to make sure. Like it's more likely that they're fine than it is that they disappeared. So we'll incrementally try more expensive ways. If that fails, if we know 3 other healthy people, we'll ask the 3 other healthy people, I'm not receiving a response from this person. Can you tell me, or can you see them and I just can't see them? Are we having a network split? And you kind of go through this process. This converges extremely quickly. I don't have the exact numbers off the top of my head, but even for a 50,000 node cluster, you could detect a single server failing in milliseconds. Rather, it's hundreds of milliseconds probably at that scale. But at maybe a 1,000 node cluster, it's very, very fast to figure this out. And it's constant, because if you have 50,000 servers and each one is randomly picking 3 servers, it's just a constant load that increases. It's not, you don't have one server health checking all 50,000 every second. It's distributed. And so that's sort of how this failure detection happens. And again, why the agent is important, because if you have, let's say, 100 services on a node, and the node is CPU overloaded, and so it's trying to perform the health checks, but the scheduler isn't giving it the time to actually perform them and report failure, the gossip layer will detect the CPU overload and mark it as unhealthy and not pull the services out. And so the agents provide a lot of value to this.
I have a question about agent deployment, where it's appropriate, where it isn't. So it sounds like you would mostly deploy the agent on services that need to talk to each other, but not necessarily at what I would think of like an end user client. So what's the discovery mechanism for that end user client that's not running a Consul agent? Would just be vanilla DNS?
Yeah. I mean, it usually is a service itself, so it wants to register with the catalog. So I would say in 99% of cases, you are running an agent anyway, because it's registering in some way. But yeah, you would have to. You now have a service bootstrapping problem that you didn't, service discovery bootstrapping problem you didn't have before, and you have to find a way to get that information in.
Okay.
DNS is common though, like because the servers, because you only run 3 to 5 servers per data center, it is pretty common to just allocate static IPs for those 3 to 5 servers and just build normal DNS entries for those, whereas your services are highly dynamic.
Okay.
And does it do we're going to communicate to the subnodes and the peers, and it's going to gossip over IPv6?
It supports
Or both?
It supports both, yeah. We did a bunch of V6 work a couple years ago, so it supports both now. But yeah, so the way it propagates membership is that, yeah, it sends, as it discovers each other, it slowly fills the membership thing. We've done some enhancements to the original protocol. Was only meant for about 50 nodes because it was written in 2001. The paper was published in 2001. This is totally not necessary for this, but we have a research team, and the research team has worked directly with the original authors of the paper. We've published follow-on papers built on top of that, and some of the enhancements we made to that from real-world stuff is, for example, we added a push-pull mechanism so that in addition to every second just pinging with UDP packets, on join and then every few minutes, we actually TCP connect to a node and send the full catalog back and forth. And so this, we found in practice, the results are in the paper, but we found in practice that this dramatically reduces convergence time without significantly increasing load.